All right, now that we know about electromagnetism, we're going to have a look at electricity and how we use it on the grid. Electric power is the amount of energy that's delivered in a circuit to a device or a load in any given amount of time. So we can calculate electric power using this formula, where P is power, V stands for potential difference or voltage, and current is represented by the capital letter I. So power equals voltage times current. Or, since we know from Ohm's law that voltage is equal to current times resistance, or V equals IR, we can substitute. So that's from Ohm's law. So instead of writing power equals V times I, we can write power equals I times R times I, which is I squared R. So we can calculate power that way as well. Or, from Ohm's law again, we can write current as V over R, just rearranging. Current equals V over R. And we can substitute that in and get power is equal to voltage times voltage over resistance, or V squared over R. When we use electricity, we're receiving electricity from other locations usually. In our case, we get some of it from the generating stations at Niagara Falls, which provide hydroelectric electricity. But a lot of it we get from Bruce County, where they have a nuclear generating station, and some of it comes from Darlington, which is east of Toronto. And so we get lots of our electrical energy from there. But we need a grid. We use the grid to distribute that electrical energy. So the power travels from the power plant to your house using the grid. So in the power plant, we use, usually we have something that's going to heat up water. So in a nuclear power plant, we have containers, large containers of water that are heated up into steam that then forces a turbine to move, and then that kinetic energy gets converted to electrical energy. Sometimes we use gravitational potential energy. So in a hydroelectric dam, like this one, it's the gravitational potential energy that gets converted into kinetic energy as the parts of the generator. The turbine gets moved by the moving water, and that's how we generate electricity in that case. So that's hydropower. This is more like what we see in using steam power. If we could burn coal to do this, although that, of course, produces lots of carbon dioxide, so we would rather not burn coal if possible. So again, in Ontario, we get a lot of that energy from nuclear power plants that will heat water, turning it into steam, which then drives a turbine to move it and generate electricity that way in a generator. We can also use concentrated solar, which is a pretty new technology in which many mirrors are used to reflect light to a container of water like this, but typically it will be in a big tower, something like this, and a field of mirrors can be used to reflect sunlight to the same place up in the tower, and that heats up the water very intensely, and then we can use the hot water in the container to drive the turbine and produce electricity that way. Now recall that alternating current, or AC, means that the current changes direction over time, and so in Ontario, in Canada rather, in North America in fact, the frequency is 60 hertz. So the current changes direction 60 times every second. And generators produce alternating current, AC. So power plants actually produce 3 different phases of AC, or alternating current, and we say that they are offset by 120 degrees. And they produce these all at the same time. So at any given moment in time, one of the 3 phases is near its peak. So that means that instead of getting power that fluctuates, you get a relatively constant amount of power all the time. Not everybody needs this, but if you're into industry, then you may have equipment like welding equipment that requires a fairly constant current flow at all times, and that will help you out there. In our houses, we generally don't need all three phases. A power plant has 4 wires then. In order to accomplish this, the 3 phases and a neutral 0 voltage ground wire that provide a return path for the electrons common to all 3. So in some circuits, the earth itself may be used as ground. And we ground all circuits as well for, you might recall, we ground circuits for safety as well. So the wires leave the generator and enter what's called an electrical substation, where the voltages are converted to higher voltages. And that's really important. We transmit the electricity with extremely high voltages, and that saves us from wasting a lot of energy. We'll see why in a moment. We use transformers to do that. And that's so that we can transmit the electrical energy over long distances of the. So the high voltage transmission lines are supported by large steel towers, and the wires at the top are ground and placed there in order to attract lightning. So we don't want to disrupt the system or damage the system by having them struck by lightning. So those wires at the top allow an easy path for the lightning to take to ground so nothing gets damaged. So why do we use the high voltage? Well, typically long distance transmission lines will carry electrical power anywhere between 150 to 750 kilovolts. Well, remember that power can be calculated by multiplying voltage by current. So the current drawn by a substation, if we rearrange that equation, is equal to power divided by voltage. But power is also equal to the current squared times the resistance. So the loss of power along the power line, which we call the line loss, is power lost equals I squared R. And when we substitute P divided by V for current, we get power squared times resistance over voltage squared. So the line loss is lowest for high voltages. If we make sure that voltage is high, we're dividing by the square of the voltage. So we have P squared, sorry about that. We have P squared times R over V squared. So if the denominator is really big, that means that the line loss is going to be very low. So we have much less wasted energy if we transmit the electricity with high voltages. And if we're using lots of power, then we'll get more line loss. So that means we have the lowest efficiency at times when we have the most demand for electricity. So that's why in the summertime, when lots of people in Ontario are using air conditioners, there's high demand, which means that the grid is less efficient. And so we have more wasted energy in the summer, those really hot days, than at other times during the year. Now, to use the electricity in the home, we can't use extremely high voltages like that because they would be dangerous. So we do what's called stepping down. So we decrease the voltage as it goes into homes and other buildings to make it safe. Before we do that, it gets stepped down at local substations to less than about 10,000 volts or 10 kilovolts. Then it gets split up to get distributed to other places. You may have also seen these on the side of the road. These are called regulator banks, and they're used to regulate the voltage along the lines to make sure that the voltage doesn't change too much. So at the top of hydro poles, you may see something that looks like this. Those are taps that split the phases because your house typically only needs one phase, unless you're doing a lot of welding. And then local transformers, for sure you've seen these. In fact, outside the school you can probably see one of these near the street. And a local transformer steps the voltage down to what is required to run household appliances. So typically 120 volts or at most 240 volts. So in North America it's 120 volts. In Europe it's higher. Most places in Europe are probably about twice that. But not all devices we have in the home require the same kind of current, and some of them require direct current, like if you're charging your phone, for example. And so we can convert alternating current using an adapter. So you've seen these before, and your phone probably has a little cube that you use that would have an adapter in it to convert to direct current. So why do we use it? Well, for one thing, electrical generators generate AC naturally. You'll remember the motor has the spinning parts, the armature that changes, so we have to change polarity of the current inside the motor to make it work. Well, the same thing happens in reverse for a generator. So as the armature spins, it naturally changes the direction of the current over time. And if we spin it with a certain frequency, then we'll get a frequency of 60 hertz for the change in direction for the current, and that's what we do in North America. In Europe, in most places, it's going to be around 50 hertz.